Okay, so let me jump back to where we were. Let's go ahead and get started. Okay. So now we want to talk about different ways of actually accomplishing the goals. And I've left some extra time for questions because particularly there's a lot of application-specific stuff. And it would be sad to end the session and then like exactly at noon and have no time to actually discuss any of that. So we might end the sort of formal session a little bit earlier than noon so that we have extra time for questions while everyone is still milling around here and still has them fresh in their mind that may be specific to your application. Okay, so and we'll probably just call that some Q&A session towards the end. So we'll talk about different ways of sort of accomplishing the goals that you're trying to reach, starting with just building it yourself, basically, DIY. It's very easy to build your own partitioned system. If you go with the fixed hash key method, just simple hash key partitioning to get the data distributed. The problem then comes around that it's actually much more difficult to do any of the additional stuff you might want to do at that point. So it's really easy to get the data distributed. That's not the hard part. That requires some code changes here and there, but in reality it doesn't necessarily give you a scalable system because the key to the scalable system is not getting more capacity. Capacity is only half of the equation in scalability. The second half of that is the ability to actually grow the capacity without any significant downtime or locking or anything like that. So it's really simple to get the data distributed out there. At that point, actually, you've probably made your life harder rather than easier, although you've gained some capacity. So what happens then? You've distributed your data across 4 servers based on fixed hash key partitioning. What do you do when you need to add the 5th server? There are a couple of strategies for that. So the simplest strategy in hash key partitioning, well, is you can never add the 5th server. You can only add the next 4. You have to double the number each time in order to make the growth somewhat manageable, because that means that you're only moving data from one server, basically. So you can split a partition. And technically you could, I guess, add the 5th, but the partitions would be imbalanced at that point. As long as you've got somewhere you've got a mapping of bucket to machine. So it's difficult to grow in a custom solution, and in fact you can spend a little bit of time actually developing the partitioning itself. The majority of the time, the sort of head-end for that is actually developing all of the advanced functionality around that. So I won't talk a lot about building it yourself. There's a couple of other solutions out there. Hibernate shards is actually a new one, and I threw it in here because it's fairly new and it got a little bit of press. In reality, I think they've implemented some of the easy problems and not fixed some of the hard problems in Hibernate shards. So if you've seen it out there, it basically it implements a partitioning system based on Hibernate and Java. It's actually kind of a hybrid between fixed hash key partitioning and directory-based partitioning. It has this concept of virtual shards that abstract things out, but it doesn't really allow you to move things easily. It's basically the bucket concept that I was talking about. You divide things into buckets called virtual shards, and then you map those virtual shards onto physical machines that are the actual shards. And the shard is sort of a synonym for partition that you'll see quite often, and in this context it's the only term that's used. But you'll see lots of other custom implementations use the term shard as well. Currently it's still painful to repartition in that model. It doesn't really offer any automatic tools to really help that along. And it doesn't handle rebalancing at all. It doesn't handle any aggregation, so all of that is sort of left to be developed. So they basically implemented the easy parts of it, which is getting the data distributed and getting access to it, but not necessarily the harder parts. How many of you have heard about Hibernate shards before? A couple. Okay. One of the projects that I would like to spend a little bit of time talking about is called HiveDB. And this is actually, I'm sort of biased because it's a project that I've been participating in and sort of guiding and such. But it's actually a lot more advanced than any of the others that I've seen out there that are open source. But it's still got some ways to go, and it's a fairly new project. So currently I would say it's better than building your own by a long shot, but it isn't. You shouldn't necessarily expect it to be fully polished and plug and play. But HiveDB is an open source project. It's designed to implement the entire sort of standard partition by key MySQL system based in Java. And you get some grimaced faces by saying it's based in Java, but if you're building something in PHP, if you're building something in Python, if you're building something in Ruby, the entire partitioning system doesn't have to be in that language. Only the easy parts of it do. And that's really the idea behind HiveDB, is that it's basically, it handles all of the hard stuff, and that hard stuff doesn't have to be rewritten in whatever language you use to develop your own application. It's something that originally, I wouldn't say I envisioned it, I guess, but sort of as a natural byproduct of working with so many customers that have the exact same problem that they're trying to solve. Telling each of them there is nothing out there, so you'll have to build your own, isn't really a good solution. So at some point, it switched into there's nothing out there, but it would be great if you built one and open sourced it. And some customers actually listened, so it is actually built and it is open source. It was implemented largely by Fortress Consulting for one of our other customers, and Cafe Press, who's got the majority of the recent development on it and really polished it up, so it's actually really nice now. And ProvenScaling has sort of helped along the way and made sure that it went the right direction and that it would end up as a scalable system. We didn't write any of the Java code because I don't do Java. I don't think Eric does Java. Many companies have already built similar systems. If you've attended any of the LiveJournal presentations, you've seen a lot of this before, but it wasn't open source. If you've attended many of the other sessions about how do we scale our site, you'll see plenty of the same stuff, same components, same concepts, implemented slightly differently here and there, but a lot of the same stuff. Just a couple of points. HiveDB is basically, like I said, many of the solutions that exist, there are a couple of open source solutions out there that do a little bit of the partitioning model. But they only really solve the easy part. They solve deciding where to store data and then figuring out where to retrieve a given piece of data. They don't handle any of the hard part. And what I would call the hard part is the ability to actually rebalance things to keep a balanced partition architecture, to be able to move individual users that are causing load problems, and to be able to implement other more interesting scaling strategies like scaling by the complexity or the cost of a user. HiveDB is really split into a couple of pieces. The server components, not so much like it's a single server that you fire up and it runs, but just the server-side components, I would guess. And then the client-side stuff. And the server-side stuff, I haven't really made a distinction as to what's a database and what's a daemon in this model, but the Hive metadata as a database basically contains the partition definition. It's just a MySQL server itself, which contains all the metadata. The directory then is the mapping of the partition keys to partition maps. So the metadata contains the data about what partitions actually exist and their current state and all of that stuff. The directory itself, which is usually running on the same machine, is the actual mapping of partition key to partition and secondary key to partition key. So the question came up earlier, if you've partitioned by user ID, don't you then need the user ID in order to log anyone in at any given time? So they would have to log in by user ID. And that is kind of true. So the secondary keys is where that gets interesting. So let's say you've partitioned by user ID. You normally expect that users log in by email address. So how do you figure out which partition they live on given only their email address? And that's what the secondary keys are for. Those are maps from anything else to the partition key it maps to. So from there you can then get to the partition itself. Make sense so far? So given an email address for a user, you do the lookup on the secondary key index, which is a very simple, essentially two-column table that maps email address to probably a big int or an int. For the partition key then maps to the ID of the partition, and the ID of the partition can be used to get all of the other metadata about the partition itself, all the way down to things like IP address and whatnot. So in order to sort of use the queen, the Hive, the only thing that you need is the URI for the Hive metadata database, which is just called the Hive, basically. From that you get the partition definitions, which gives you all of the other URIs to everything else. and gives you access to the full Hive. So within the application itself, you have a reference to the Hive URI and nothing else. Yeah?
Does Hive actually cache any of that directory? Or
Sort of. So yes, but it's an optional piece, basically. It doesn't have to. It isn't implied that it's always cached, but it is integral to the system. That if you built a Hive DB system, you would probably use memcache to do the cache of the directory. And it's built into the API and such that it will automatically check the caches and purge them and do all of that stuff. So it is assumed that you'll probably cache it, but it isn't required. So that's all the easy part. Those two components really just implement a sort of normalized and reasonably well-designed partitioning scheme based on directory server. So exactly as I've been talking about. The hard parts that you really need to build on top of that are the following ones below that. The Hive Queen, which is the management system. That's a component that basically decides how to partition the system and how to repartition the system at runtime, effectively. So it can actually collect statistics based on essentially callback functions that you create. So you can collect statistics on how expensive a user is and then use that knowledge within the Hive Queen to decide how to rebalance. So typical schemes would be, let's just say, the most naive and simplest is just say, make sure that there are approximately the same number of users on each partition. So then when you add the fifth partition to a 4-partition system, the Hive Queen will automatically handle moving a quarter of the users from the other partitions in the background as a lazy process over to the new partition. So you don't really have to do anything special to grow. It can also do a lot more complicated things. You can actually implement some functions to say that we want to balance users based on their cost. So if a user has 1 million photos versus if a user has 5 photos, clearly they have different costs. In an optimally scaled system, given that those users are equally active, and the likelihood that they are is actually fairly slim, but if we make lots of assumptions there, if we assume that they're equally active but that their real cost is in storage, for instance, then we can make, the optimal way to partition them would be to balance an equal number of expensive users and an equal number of non-expensive users across all servers, so that the expensive users get full use of all hardware and the cheap users get full use of all hardware. Some alternate strategies which are also possible in that model are to archive old users. So we can say that a user, after they haven't logged in for a month, they're an inactive user, and we could potentially move them to inactive user partitions. So that is actually a fairly compelling reason to use this whole complicated system, is that you can actually say, in a given website, typically you may have 10 million users, but in reality, how many of those users actually log in once a day? How many of them actually log in once a week? How many of them log in once a month? If you look at those numbers for most websites, it's not a huge percentage of the overall number of users that you have registered effectively. So it is fairly compelling to start moving archived users over to slower hardware. And that doesn't necessarily mean old hardware, just hardware that's designed to hold an archive rather than active, busy users. So keep more cheap users on bigger disks, slower disks, fewer number of machines, and have the nice, fast, new hardware available completely for all of the active users only. So the Hive Queen system really makes decisions. It doesn't actually follow through with any of them. It uses a job server to do that, which is based on ports, that actually executes the tasks. So the Hive Queen just creates tasks and inserts them into a queue, which you then have fairly good control over how quickly they're executed and priorities and that sort of stuff. So you can then start and stop the jobs whenever you want without losing any of the state information as to why you're doing it in the first place. One of the other pieces that I've hinted at so far, but I haven't really talked about, is this whole concept of aggregation. And that's another one of the hard components that no one has really done yet. It hasn't been done in the HiveDB model yet, but there are some provisions sort of in there, and there's been a lot of discussion as to how it should be implemented and when it should be implemented, but it just hasn't been done yet, which is the aggregation layer. The idea for the aggregation layer is basically that it's a middle tier that sits above your partitions but below your applications. So rather than connecting to the Hive directly, you connect to the aggregation layer, which then uses the Hive APIs itself to contact all partitions or a subset of all partitions to do aggregation-y things. So if you need to do like, select the average number of friends from users grouped by state, that's something that the aggregation layer would do. You would submit a single query to that. It would actually contact all Hive partitions in parallel, execute the appropriate modified queries, and then aggregate the results back to you. And that solves two problems, which is moving that ugly bit of code out of your application, because you definitely don't want to do that every time you need that in the application. And being able to do it in parallel, which isn't that easy in things like PHP, but is incredibly easy to do in Java, for instance. So doing it in Java as a separate daemon that runs probably as a web service is actually fairly compelling. Then the API in PHP would just connect to the web service. Questions so far? All right. On the client side, whenever you need to use the Hive, you don't have to know about all of the different components to it. You would actually just connect to the Hive API. You use a single URI, which gives you the metadata effectively, and from there, the API itself manages connecting to the right nodes, the right partitions. Once you've established a connection, really how this works, you ask for a connection based on partition key or based on secondary key value. So you can say, get connection for key, and you pass in all the other stuff. The key that you define may be user ID, so you could say user ID 5. And it will actually return you a JDBC connection for user ID 5, which you can then do whatever you want with. So you use those direct connections to do the actual work within your application. And in typical cases, you would probably build some sort of abstraction on top of that that's application specific. So rather than within the application always requesting connections by key, you would actually build methods on top of that that do all the underlying work, of course. The Hive API itself is really the only piece that is sort of development language dependent. And the end idea is that that actually should be written in each language. The API itself should be written in Perl, in PHP, in Ruby, etc., based on the reference implementation in Java. Currently, there are some people interested in doing it in PHP. There's a couple of people interested in doing it in Ruby. No one's actually started any of those projects. So the only API available right now is Java. Questions about any of the partitioning implementations?
Does that automatically pull connections for you?
Sort of yes and no. It can. How about that? It isn't. Most of the sort of questions like that, actually, I would say it would be it can. There's a lot of things that it can do, but they're not required in the system. It's just a matter of how you define your configuration and how you define some of the setup code. So exactly which driver should be used, for instance. You can use the MySQL driver, or you could use a connection pooling driver.
But I'm thinking of a web page which is executed for one user, and then the next hit the next user, and he's got to switch then quickly between connections. Basically on each hit page, he's got to get a connection.
So I would say in the actual implementations where this has been done, yes, it does use connection pool, and it works very well. Yeah.
How would you describe the stability of Hive?
It's a bit of an unknown. It's in production in a couple of sites, but like I said, it's a new project, so it's better than writing your own, but not necessarily polished. Definitely, I mean, it's a complicated enough system that even if you just implement the easy parts, it's going to take you a while, and it's not going to be any more stable. So I would tend to sort of push people towards using an open source project for any of this sort of stuff. And that's really the only reason they would create it in the first place, is to try to get people to sort of standardize on one way of doing the partitioning, and hopefully write the right way for most applications, and get some actual movement behind it so that the project can continue and get a lot better and get a lot more people going. Realistically, the answer for if a customer asks us how do we build our system, if at some point probably within the next few months, actually, the default answer would be just use HiveDB. That would be fantastic because customers don't like hearing, well, there isn't anything good, so build it yourself. Yeah.
What can we read more about
HiveDB.org. I think it's even Googleable now, but HiveDB.org is the actual site. And I realized this morning, long after this went to the printers, that I didn't include the URL in the paper, but HiveDB.org is the one. Yeah.
Is it like ready to play?
Yeah, the code is available. It's on, if you go to HiveDB.org, there's some URLs to Subversion repositories, so you can download the code and play around with it. There's a test case that's included in it called Playlog. Well, it's not really a test case, it's more of an example application.
And the API also is like the Java API?
Yeah, it's all there. Yeah. The only thing that... the site's fairly new, so and there aren't a huge number of inbound links just yet, so Google isn't too happy about it. Questions about anything with regards to partitioning just yet? So as I said earlier, we'll actually, this is sort of the end of the partitioning part of the talk. We'll talk a little bit about high availability and the options you have there, and then a little bit about how to combine them together into one single scalable, highly available system. Yeah?
Just a quick one about Hive. Does it have a sort of built-in support for affinity?
Not exactly. It has some defaults. So the way that you choose how or where a record goes is pluggable, and the default is just random. But you can, well, it's random based on which nodes are available. So you can actually make one unavailable for new data, but you could also write your own that understands affinity. Yeah?
You said earlier that reporting might be a problem with partition. So could you comment on some ways to get around that or some techniques?
So the reporting is always going to be difficult in a scalable system, sort of partition system particularly. The right way to do it is basically to have a single component, and that's the aggregation layer that I was talking about with HiveDB, which isn't written yet, and should be within the next few months, I would guess, but it doesn't exist right now, so it's not going to help you right now. I would say if you're really interested in doing that, maybe get behind the aggregation part of the HiveDB project and contribute some effort to that and make sure it does what you need it to do. The end idea is basically that you could submit a request, an aggregation, some sort of aggregate query, and it will actually do all the work for you and return a single result set handle. So it shouldn't be any more difficult to use than your currently unpartitioned database. You'll get the result back probably as like a web service result or something like that rather than MySQL result set, but other than that, no real difference. Okay. I talked a little bit about, I talked a lot about replication, and some of these slides were used last year. If you attended my talk last year, so you've probably seen a couple of these, but I've included some of that content just to frame the whole high availability scenario with regards to the scalable systems that we've been talking about. So just to start off with a few of the goals around high availability. And the interesting part to start with is just, as I mentioned at the beginning, high availability is a relative term. Well, high is a relative term. And if you just say availability, availability is a relative term. So one of the hardest parts of building any sort of system like this is just determining how highly available do you need something to be. And actually being honest with yourself and with your managers and everyone else about what the actual requirements for the application are. Because in many cases, you could say, we can't have any downtime. And if you ask a product manager or something like that, that's what they'll tell you. We can't have any downtime. It's not acceptable. But the reality of the situation is that in many cases, you have to trade downtime for future availability, basically. That you have to take some downtime today in order to not have a horrible meltdown later. So you have to keep those sorts of things in mind. Some of the goals around this, the obvious goal, if you say high availability to anyone, the definition they'll probably come up with is something similar to avoiding downtime due to failures. That's really only maybe a half or less of the big picture, because in reality, failures are they're fairly common in a given database system with multiple servers and well configured and all of that. The most common failure you'd ever encounter is probably a failed disk. If you're encountering other failures like power supplies or CPUs or memory very regularly, that's usually indicative of other problems within the larger system or bad hardware or something. So typically in a database system you will have failed disks. And typically the RAID system that you hopefully have running will handle that failed disk gracefully. You'll be able to swap it out in due time and have the RAID rebuilt and all of that stuff, or have the disk rebuilt without any sort of actual downtime. So the most common type of failure, actually, hopefully, you've designed around already. So when we talk about failures, in that sense, what we're really talking about is an actual failure where the system just goes down. That could be a double disk failure in a RAID, which are infrequent but do occur. That could be something like a power supply failure where the machine just shuts off effectively. Maybe you have bad power, unclean power. Maybe you got a batch of bad RAM and you have some RAM failures and the machine kernel panics. Anything like that where the system is just down. And we'll talk about how to handle both of those cases. So they're slightly different. Normally for things like single disk failures, you don't have to do anything. Not that you don't actually want to do anything, but you don't have to. So when we build a system, we don't want to have single points of failure, and in general, like I said towards the beginning, you would want to sort of make a list of, what are the single points of failure in my system, or, for the parts that aren't a single point of failure, what is the transition time? So we have a duplicate, but how long does it take for the load balancer to fail over? How long does it take for the MySQL system to fail over? There's a lot of sort of time-related things there as well. So even if you design the system such that everything is redundant, that still doesn't mean you're going to have 0 seconds of downtime. It just means that you are going to have some measurable quantity of downtime, that you know that it will take 30 seconds to fail over, for instance. Overall goal, of course, is speed. We want failover operations in general to be as quick as possible. So when we design the MySQL failover part of it, we want that to happen as quickly as possible. One of the things that allows us to do is to use it in many cases where there is not an emergency. So I'll cover that in a moment. And 2 points that I could reiterate again when you design an HA system, failover and such. Try not to use DNS for the actual... You can use it for pointing to IP addresses. That's what it's for. Don't use it for failing over roles between machines. And no dependency on code changes to have a failover either, because that tends to cause problems like accidentally rolling out new code or dealing with the problems of atomically updating the code across potentially hundreds of web servers or application servers. One of the really nice things that you should try to design into the HA system, depending on what you choose, is to allow for casual failovers for things like upgrading hardware, changing out hardware, moving to new hardware, for instance. If you need to move to a new database server, what is the process for doing that? Some of the failover systems handle that more gracefully than others. Yeah, so there's another part which I'll definitely come back to in a moment, but part of that is for maintenance as well. Some of the failover models allow you to do schema changes without downtime, and most of them don't. So we'll talk about what the options are there. And the last point is basically just don't design one-way failover systems. Those are almost always a disaster in production. So just being able to fail over, for instance, from master to slave. Yes, you failed over, but what now, right? How do you get back running in the same scenario that you were to start with? If you don't have a good plan for that, you don't really have a failover system. You have essentially a disaster recovery system, and probably not a very good one at that. We'll talk a little bit about MySQL replication, because understanding some of the basics of MySQL replication is really kind of required to understand the other failover processes and the trade-offs and such that you make at various points. So just some basics about MySQL replication to make sure that everyone's on the same page. And I've actually cut most of the content out of this, so pretty simple stuff. MySQL, the replication that MySQL itself includes is master-slave, one-way asynchronous replication. So you have a concept of a master, you have a concept of slave. The slave connects to the master, it asks for the logs from a certain point. Those are called the binary logs or bin logs. You'll hear that term quite often, bin logs or binary logs. So the slave connects, it asks for the logs from the last position that it was reading from, and it starts pulling those down in real time and executing them. That's really all there is to replicating. All there is to it to replication. It's very, very simple. There's a lot of optimizations, obviously, in that whole process to make sure it happens really quickly. In reality, it's almost always within a few milliseconds of each other, given a reasonable system that you're trying to replicate, and not terribly overloaded or anything like that. So the slave requests binary logs from the last position it knows about. The master sends them down in perpetuity. The slave doesn't have to request each new change or anything like that. It doesn't pull the server. It's getting the changes in real time. So the actual delay from changing something on the master to getting it replicated can be less than 1 millisecond. Replication works with all table types and mostly all features. There are some quirks here and there of features that don't work at all or quite right with replication, and we won't spend too much time talking about those. The other key point, any replicated system, and this goes particularly true if you're just doing simple master-slave replication, anything that you would consider critical, anything that cannot return stale data, you have to do that on the master. You can't send all reads to the slave once you start replicating. The typical thought is basically you build, if you start using replication, you set up your first slave, you start sending all reads there. So anything that starts with select, basically, send it to the slave. And in fact, there are some sort of middleware pieces that just check to say, is this a select? Send it to the slave. That's a really bad strategy and will annoy users to no end, because you may have just written something, and particularly when load is heavy and replication may fall even just 1 second behind, the amount of time it takes from writing within let's say a PHP process, from writing to the master to a few lines down, reading that same data back from the slave to format the rest of the page, it may not have made it there yet. So anything like that would have to be done on the master. Anything where you just need the authoritative source has to be done on the master. Anything where you need to depend on the database doing any sort of row-level locking has to be done on the master. Because certainly there's row-level locking happening on the slaves, but you're not blocking any writes other than the ones coming from replication, so you're not really buying it. So critical stuff must be done on the master. In a typical just basic replication setup, you have one master, which is your single source of truth, and you have any number of slaves, and I'll show some examples there. The slaves then are used for reads only, and only non-critical reads. All writes and all critical reads end up going to the master. So there's a few topologies you can use, and these are just examples of basic replication setups. So the very basic building block in replication is a simple master-slave. So one-way replication, there can be delays, it's asynchronous, etc., etc. You can set up lots of slaves, and this is a good model if you're trying to do something like news distribution, or in any case, news is a good example of this, but you have a limited number of publishers and an unlimited number of consumers. This replication model works really well. Where does it not work? Any ideas? It might be worth a bottle opener.
Heavy writes.
Who said that? Yeah. Okay. Right, heavy? You can both get one. There you go. Oh, almost got your coffee with it.
That's okay, it's empty.
Oh, thanks. So, it doesn't work with heavy write scenarios. Why? I didn't see a hand go up for that. Go ahead.
Slaves are serialized.
So they're executing everything in serial. That's one reason, yes?
Every write effectively in this case becomes 6 writes.
Correct. So every write goes to all the machines anyway, right? So you're not buying any scalability with writes. All you're buying is distribution of data. So it's a really good way to get data from one point to any number of points really, really quickly. And in fact, there are a few systems in various companies that do exactly that. They just use it to distribute stuff. Forget about the fact that it's an actual database that you're dealing with. I need to distribute a file to 200 machines. MySQL replication can do it within a few milliseconds. There aren't too many other systems that can promise that. So. Yeah.
The other problem arises when all slaves, because I've seen this, are writing to the same SAN, like the same disks.
Sure. Yeah. So if you're trying to build this on a SAN solution, you may be sharing disks among those slaves, and the slaves aren't going to execute the writes in any more efficient way than they did on the master. So they're all going to be doing the same work. They can't share storage. MySQL doesn't allow any sort of, no storage engine in MySQL allow shared storage. So they all have to have their own independent and writable storage. Yeah.
You might think that 200 milliseconds is a really, really short amount of time. But if you're doing something like all your reads from the slave and all your writes to the master, you may end up finding that if you do something where you have a page and you update information on that page and then you reload that page again, if you're doing those reads from the slaves, you're going to end up finding that it didn't really update and it might take, another refresh.
And there are an inordinate number of websites where you can see exactly that, especially as they first start scaling and that someone figures out that you can do MySQL replication. So they throw it into production, and then as the system gets busier, maybe when you were testing it and when you're in QA, no one notices because replication is not busy enough to actually get behind. Once you throw it in production and you have some peak traffic in the morning or something like that, and it gets 2 seconds behind or half a second behind or something like that, it really starts being noticeable. That not only, it's not that the page isn't loading quick, it's loading really quick, but it's loading the wrong data. So, not really an acceptable scenario. Okay, good enough? So you can do this concept of a relay slave. There isn't actually an official term for this. I use the term relay slave, but it's really just a machine that is both master and slave. So it is reading from the master above it, it's storing its own binary logs and such, and the slave below it is replicating from it as though it were the only master. So it's effectively just passing on the data. And for just passing on the data, actually, MySQL doesn't do it terribly efficiently, but it does actually execute everything, and there's some tricks you can do to make that more efficient. But nonetheless, we can just assume it's in the same configuration as the others. It's purely just passing on the data. This is actually useful in scenarios where you have lots of slaves. And if you're talking distributing, a 4 megabyte file to 500 machines, probably not the best idea to connect all 500 slaves to one single master and expect it to not get overwhelmed when all of them are trying to pull down the same replication stream at the same time. But you can actually set up so you could set up 5 relay slaves, and each of those could have 100 slaves connected to it.
I think it's worth noting there that if you're going to have one relay slave, you should always have 2, because if that one goes down, all of your slaves stop.
Correct. So if you're trying to distribute to lots of machines, you should always have more than one relay slave, because it is a single point of failure in the chain of replication that could affect. So if you put 500 machines behind one relay slave, you would take them all out with a single failure.
I'm trying to understand, what's the point of having a relay slave again?
Really, the idea behind it is just either distribution to large numbers of actual slaves or distribution to slaves which are in sort of disparate geographies. So if you try to set up 50 machines in India connecting to one machine, replicating from a machine in San Jose, having all of those 50 machines replicating across that link is both not going to be very cheap for you and not going to be very quick.
You get the same problem with the relay slave. It's just also not your master where people are also trying to do writes. So you're separating the service of the write database and the database where you get the replication from, right? Is that right?
I didn't follow.
So with a relay slave, it's not any less expensive because it still has to go through the pipes and whatever. You're just not doing it with so many.
Correct.
You have one thing. Yeah. So you're taking the service of, hey, replicating the stuff, putting it on a separate machine, so you're not taxing your master more.
Correct.
Hey, Jeremy.
Sure.
Maybe you could explain to people why having a lot of slaves reading from a master actually puts load on the master.
I could, yes. So, and that's actually not a terribly easy question to answer in most situations, but what I usually tell customers with regards to, how many slaves, the common question is actually, how many slaves can you have? And that's sort of the root of that question. And what I usually tell customers is that the first slave has a very, very real cost, primarily because you have to have binary logging enabled, so you may not have had that on before, and it will also be doing some extra reads and such. Additional slaves don't add terribly more overhead, but what they do add is additional network overhead and additional context switches, basically. A little bit of additional memory for the actual connection, and depending on how large objects you're replicating, potentially a lot of additional memory. But given trying to maintain a replication system where the delays are a reasonable amount, if you overtax the master, and that will happen based on, if you have 50 slaves, whenever a new write comes in on the master, it's written out to the binary logs, and then all 50 of those replication slave threads get woken up simultaneously to try to replicate the data. Given that you probably only have 2 or 4 CPUs available, you can't really have 50 of them all running simultaneously, and given that you only have so much network bandwidth available, you can't have them all transmitting simultaneously. So at some point, there's some sort of logical limit that you hit where you actually start adding delay by adding more slaves. You don't necessarily add tremendous amount of load to the master, you just add delay. Does that summarize what you're thinking? So I would say that the actual cost of adding an additional slave after the first one is not very large. The cost of adding 100 additional slaves is fairly large. Yeah?
You could also use relays to filter subsets of data out. So for instance...
You can. Yeah. See, replication allows you to do all kinds of interesting filtering on both what gets logged in the first place and what gets replicated once received. In all cases, though, the way that that filtering is implemented in the logging and in the execution is not really optimal until MySQL has robust change-based replication. So you can do things like filter out individual tables. But it's very easy to write a query that crosses the table boundary. So a query that uses 2 tables or a query that uses 2 different databases, for instance. And all of those sorts of operations will break replication if you have any sort of filtering that involves only part of what you're changing or what you're reading from. So a good example of that is, well, there's 2 reasons for that. One is a lot of systems, they try to filter out like development databases, for instance, so they're not replicating a development database. In other cases, you try to filter out just certain parts of the data set, so you're not replicating as much data. If you try to do something like a insert into select, for instance, and one of the tables, either the one you're inserting into or the one you're selecting from, is not replicated, you will break replication. And actually, a bad example of that was trying to filter out development databases, and then at some point along the way, there was a batch of, 5,000 records that needed to be deleted. So someone wrote I guess it was a subselect that deleted from the production database, but of course, since the user that needed to do the delete of 5,000 records, they didn't want to create a new table in the production database because that's a sin. So instead, they created a new table, inserted their 5,000 IDs in their development database that they're supposed to be mucking with, and then issued the subselect delete against the production database. And of course, it breaks because they're filtering out the development database. Not that it was a good idea to have the development database and the production database on the same machines in the first place, but that's a very real scenario where there's no good way to recover from that. So now all of your slaves are broken. The master is okay. All the slaves are broken, and they all need a new copy of the data, or they need you to manually delete those 5,000 records not using the development database.
Also, the more different types of slaves you have inside a replication setup, the more different types that people have to think about when they're developing applications. So going from a single master to a single slave is usually okay, but when you have a slave of type A, type B, and type C, figuring out which connection handles to use and what exists on the different slaves becomes really confusing.
Yeah, so that's a code problem, a sort of development problem, but it's also an administrative problem because you can't use the images of those slaves potentially to set up other slaves because they may not be the right type, and you can't use them to recover the master because they don't have the entire set of data. I would wonder if you have data that's sort of separate enough that you would want to filter it out in replication. if it wouldn't be a better idea to run it on 2 different instances and replicate everything on both instances. Yeah?
Wouldn't you reckon, wouldn't row-based replication actually solve that problem?
Yes, it does. So the row-based or change-based replication, which is new in MySQL 5.1, does address the problem of being able to effectively filter. I would say that the current implementation isn't nearly advanced enough as it needs to be in order to do really interesting filtering, but it is getting there and the potential is there to do a lot more interesting filtering and to be able to start recommending that people do filtering. Right now I would say I wouldn't recommend that you filter anything ever unless you have a really, really compelling reason to do so. Once row-based replication is there and stable and robust, go for it. Sorry? Yeah?
On the relay slave, would that be a good place to use a black hole storage engine?
Potentially, yes. I'm somewhat leery of it, though.
You're afraid you won't get your data back?
No. It's more a matter that you lose one usable copy. You still end up in a scenario where you have to replicate to that machine, but you lose the usable copy of the data, and you may end up with lots of interesting side effects, and you also end up with an administrative headache, because when you go to change the table type of all those tables to black hole, it will automatically get replicated by default, so you have to manage that you don't alter the table or that you don't do anything like that on the black hole slave. It's more an administrative issue than a technical issue. If there was a sort of InnoDB table type, for instance, that just threw away the data, that'd be perfect. But having a different storage engine and different semantics and such to try to do that, I'm not so happy with. Okay, so these are all the basic replication setups, and we haven't talked anything really about high availability yet, although this does address a couple of questions that came up during the break, which was, how do you scale something with, that isn't terribly write heavy? This is great for that. And you can really set up basically infinite numbers of slaves, because you can actually chain them as far deep as you want. So you could potentially distribute to tens of thousands of machines if you really wanted to. Where things get really interesting for me, though, is that if you take the basic building block that we talked about to start with, this concept of master with one slave, and you keep in mind that a slave can also be a master in this concept of a relay slave. If you take the slave at the bottom and make it the same machine as the master, you end up in a dual master scenario. So they're both effectively relay slaves, they're both masters, they're both slaves, but they're both masters and slaves of each other. Why is this interesting?
Because
how many of you have seen dual master, actually, just as a poll?
I use dual master.
Perfect. Yeah, why is it good?
Why is it good, or why is it, well,
why is it interesting, rather?
It's interesting because you can now distribute your writes, but at the same time now you have to pay attention to your auto-increment value, auto-increment increments, and auto-increment offsets, especially with more machines in the ring. And you also have to make sure that you don't execute the same server ID statements in the bin log going around, or else you're going to get these nice little infinite loops.
Okay, so there's a couple of interesting points that came up there. You mentioned writes. Do you gain anything?
Yes.
Load balancing? But are you balancing load?
Yes.
Or are you just balancing writes?
Well, load in general.
So when you build this model, if you write to both of them, you're actually not gaining anything in scalability or availability or capacity or anything. You're actually losing capacity. And you're losing another interesting part, but I'll come back to that. So.
You do gain latency. So, sorry.
Yeah. there were two hands up. I think I pointed to him, but you talked. But that's okay. Go ahead.
So you do gain latency. So if those masters were in 2 different co-locations, for example, your clients could write to the local one.
You gain locality.
You gain locality.
Yes.
Which is small damage.
Yeah. Good.
I think you might be able to gain a little bit of simultaneous writes in some of the engine tables, because the replication is serial versus concurrent writes.
Correct.
What happens on one of the masters. If they go to 2 different masters, then they can complete at the same time and then replicate go.
So I would say yes. I'm not sure that you necessarily gain though.
Jeremy?
Yeah.
I mean, you would be able to handle little peaks better with the system because the replication is supposed to then happen in the background.
So you can
out the peaks a bit.
You can even out peaks a little bit at the cost of the masters being out of sync more with each other. So the few points that I had in mind here. So you don't gain any actual scalability in writes because both machines still have to do the same work. That won't be completely true once there's change-based replication, potentially. Change-based replication can optimize some of that a little bit. Not great until we have change-based replication in parallel. Then it will be a little bit better. And depending on how your system is bound, it's probably I/O bound, so you may still not gain any actual capacity. So both machines still have to execute the same queries, they still have to do the same work. So what you've effectively done is you've made it so that you don't have to think about which one is up, basically. By putting a load balancer in front of them, you can write to both without worrying about which one is currently up. What you lose in a big way there is having any single source of authority. Now you have none. So once you write to both of them, there is no good way to tell whether a record truly exists, for instance, or how much data you've lost if one of them fails. Make sense so far? So what we typically recommend is use dual master, and we'll come back to that in a little bit, but use dual master, but write to only one at a time. And there are various ways to deciding which one to write to. There are a couple ways that I mentioned already that don't do DNS. Don't have master or writable or something like that as a DNS entry. DNS has a whole slew of problems. Don't hard code it and have to change code, or don't put it in a code configuration file and have to change that. The best way that we've found so far to do that is to use IP takeover, which basically means that there's an IP address, a VIP, that floats between the two machines, and whichever machine has the IP address and is configured correctly and all of that is the writable machine. That's a good way to ensure that, at least in a reasonably configured network, that only one of them has the IP address at any given time, and that you are always writing to the right machine. You can then actually set up slaves against these masters. Currently in MySQL, this really is not optimal at all. You can have slaves, but the way that replication is done is based on log file names and positions. So these slaves are not portable between the two masters. You can't take a given slave and move it to the other master very easily. You can actually do it, but not while the system is in production and accepting writes and such. So you can actually stop accepting writes, wait until the slave is caught up, and then you can move it wherever you want because you know the log position it should restart at. You can't easily just pick it up and move it in the middle of production, and you can't deal with the case at all where one of them actually fails. You can't do much at all with the slaves of the machine that has failed. You have a question?
Well, you kind of answered it, but I was going to say that generally I just write bash. I've written a lot of bash scripts. It locks the tables off both masters, will swap the slave over in less than a quarter of a second.
Yeah, so it certainly is possible. It just isn't sort of built in. And then that's been a discussion that's come up actually at the last 3 user conferences maybe, and nothing has been done about it. But that MySQL does not have any sort of globally unique ID for a replication event, or for a transaction even. So there's no good way to pick up a slave and connect it somewhere else and have it get back in sync. And there's no good way to take two machines that are not currently connected to each other and resolve their differences so that they can connect. So since it's based on log positions and stuff, you can do this, particularly if you need to scale reads as well as scaling writes. There's some better solutions to that potentially, but one of the most common reasons that I see this model used is just with a single slave somewhere that's used for reporting. So you have the dual masters for production, and you have a slave connected somewhere that isn't really critical, but is an online copy of the data for reporting purposes, replicated somewhere else. Yeah?
So do you really recommend dual master model?
I definitely recommend dual master model. I just don't recommend writing to both. The dual master is actually great. It has a lot of other administrative things, and we'll talk about some of that as well. But writing to both in general, is more of a headache than it's worth. It gives you, it gives you some flexibility and such in the application, but it is a headache as far as administrative tasks, taking backups in a consistent way, resolving problems when there's a failure, all kinds of interesting scenarios. Another case that can happen, actually, if you write to both, since replication is asynchronous, there is no guarantee that the other master has received any given piece of data, and it's actually possible with enough load to get them out of sync with each other irrecoverably. So normally in replication, it's possible for the slave to get behind. And there's no good way to resolve that. It's just a problem inherent in the replication model itself currently. So it's always possible for the slave to get behind, but if you have both of them as masters and they're both slaves, they can get behind with each other so that they're no longer anywhere near in sync with each other. So you can imagine like them being 5 minutes out of sync with each other, but one has 5 minutes of differences that the other doesn't have, and the other has 5 minutes of its own differences that the other doesn't have. And it's a huge mess to resolve. Yeah, question?
I've seen it before to use for multi-component applications, where each application will have a shared sets of tables between each other, and each component is responsible to write into its own master on those tables.
Okay, yeah, I mean, that would be sort of okay if you have, in the case you have dual masters, you have two different systems effectively using the same database, but they both need each other's data, but not necessarily the newest data. Then that would be sort of okay to write to both in different databases. I don't know that I would still necessarily recommend it, but I could be convinced either way, I guess.
Well,
yeah.
Each master has its own authority for that application, so if you get out of sync, you can...
I guess the only reason I could see doing that is if the two masters are in very different geographical locations. Because you're not going to gain any actual scalability from it, or any capacity from it, since they're both doing the same writes. Even though they're going to different databases, they're both doing the same work.
Well, there's also filtering. They're only replicating certain tables that have.
Yeah, I would still wonder if it's a good solution. I would think there are solutions that you could implement in that case that are easier to maintain. And I would say in all cases, particularly when you start building HA systems, it's almost always better to err on the side of ease of administration versus absolute best performance, or versus any other number of metrics you could go for. So go for ease of administration, because when the thing actually breaks, if it's really complicated, it's going to take a lot longer to fix. Yeah?
On the recorded slave, you get a different indices than on the master.
You absolutely can. Depending on the scenario, there's no reason you couldn't. But if they're useful indexes, again, that may be a case where, depending on the number of indexes you would intend to add, it might be better just to err on the side of ease of administration and make the masters identical to the slaves. Because the cost of that index is not going to be huge. And if you expect the slave to actually keep up, it's going to have it's going to have to be able to execute the queries quickly enough. So if they're enough of a cost that you couldn't add them on the master, it's unlikely that the slave is actually going to be able to keep up. Does that make sense?
I asked because we have full text on our site, but we wouldn't need it for recording and stuff.
So you want fewer indexes on the slave?
Fewer and maybe different.
It's definitely possible. Yeah, I wouldn't have a recommendation either way, I guess. Yeah. Other question out there somewhere? Nope. Okay. Oh.
Yeah, I just wanted to point out one thing. A lot of some of the things that I've been noticing, people were discussing using master-master, trying to write to both masters at the same time for the purposes of improving the scalability of writes. Where I think in most instances what you want to do is actually partition that data, as you were talking about earlier on in the tutorial. And then once you have multiple partitions, utilize this replication on each of those partitions to ensure high availability of each of those partitions.
Correct. So that's actually the end where we put it all together. Yeah. You've skipped before.
No.
That's good though. You're thinking ahead. So it's also possible to set up replication in a ring. I would say in general, don't use this unless you have a really, really good reason why you need it. It doesn't give you any extra write scalability. And it causes potentially very, very large problems in figuring out what data a particular machine should have. Yeah?
Sorry, since this is kind of a tutorial, with that in mind, what would be a really, really good reason of using this?
Haven't found one yet. The only thing I can think of maybe is using a ring where you have different databases in multiple geographic locations where, I don't know, I still think you'd end up in a case where you'd end up with a disaster scenario for actually recovering the system. Because if they're in disparate geographical locations, it's going to be that much harder to sync them together with each other because you probably have lower bandwidth and much higher latency and such. So, yeah, ugly scenario. Yeah. How much fun is it?
Awful.
There you go.
I've done it too, but I mean, I've had a ring of 5 machines before, but one of the problems that I specifically encountered, especially for very, very heavy writes, is whereas you've got 5 threads writing to one master, the slave thread is only one single thread. And I don't know whether that's the reason why it kept falling behind, but it seemed that for every 5 queries, for every 5 inserts going in there, it was always falling a second behind for each one.
Yeah, I wouldn't expect it to fall behind necessarily, any more than replication normally would. So I would say that the ring model, actually, the only thing that keeps me from saying, besides just having 3 or more machines, but if replication had a globally unique transaction identifier, and if replication allowed you to have multiple masters, you could connect 3 or 4 machines in every possible combination, such that it replicates essentially as a mesh. And that would actually be much more reliable. In the model that it is now, it's a single direction around the ring, sort of like token ring, where if one person unplugs their network cable, the whole network goes down. And I think we've gotten far enough away from token ring that we can understand what the problems with that model were. So if you have one failure and you have 5 machines in a ring, actually the other 4 machines are in various different states, particularly if you're still writing to all 4 of them. Yeah?
I have never used the circular replication. What's the mechanism that prevents the original master from feeding up?
Very good question. So that's just a sort of a general replication thing. Each server has a unique server ID, but has a server ID, which you are required to make unique. So provided that you give each server its own unique ID, it will use that unique ID to determine once the queries get back around in the ring. So the green one here, it writes something, it gets replicated over to red and then over to blue, and then it comes actually back to green. Once it receives something, it's stamped with a server ID. It compares the server ID to its own server ID, and if they're the same, it throws it away. This also has very interesting repercussions if you have a complicated replication scenario and you don't have unique server IDs. So if you have 3 machines as a relay slave, just a simple relay slave model, replication will actually refuse to connect 2 servers directly together with the same server ID. When the slave connects to the server, it gets the server ID of the master and compares it to its own. If they're different, it aborts and gives you a pretty error message. But there's no indication that, within multiple levels of replication, that they're all definitely unique. So in this model, if we have master with server ID 1, the relay slave with server ID 2, and a slave with server ID 1, everything will be connected just fine, but the end slave will not execute anything. So it will receive everything, it will show it's up to date, it will say slave IO thread running yes, slave SQL thread running yes. Its load average will be 0.00, and it will not be receiving anything. And you won't be able to figure out why. Yeah?
Along those lines, I've noticed that in order to, when you're doing these setups, you generally have to set the parameter replicate same server ID equals 0. Is there...
Replicate same server?
Oh, it's called replicate same server ID 0. That means that when it comes,
I can't say I've ever heard of that option.
Oh, okay, well.
There's a log slave updates.
No, that's for replicating from yourself.
Yeah, that keeps it, that's generally the only thing you have to add.
I was going to ask if there was a good reason for it to ever be 1, but...
I don't think I've ever heard of the option.
Even Google.
Is it documented?
Someone just posted it on Planet MySQL, I think.
Really?
Yeah.
Sounds really scary.
But generally, it's supposed to be if I, the replication slave, see a bin log statement that's mine,
Still replicated. Yeah, or still executed. Yeah.
So the manual,
don't execute.
The manual says it's only useful in rare configurations, but it doesn't say what any of those configurations are.
It's useful for when you're replicating from yourself.
Replicating.
Why would you do that? Well, what if I have?
You did rewrites in the database names?
I have a data. Well, yeah, if I have a dating site and I want people to be able to update their personal ads, but I want people to be able to search it too. So I'm going to have an DBA table on the ads, and then I'm going to have a full text table where they search it. I want to maybe replicate from myself.
I would quit. Actually.
I would hire review developers, yes, but you know there are some reasons that kind of thing.
Okay, fair enough. I can see that there are definitely scenarios where you could use it. I wouldn't say that there are scenarios where it's useful. Okay, so we look at this from the HA perspective. So far it's just been replication, and we actually have like 18 minutes to go, so we should hold off on some of the questions for now. So we look at it from an HA perspective. Using dual master in an HA scenario, we have two machines configured with independent storage as master and slave of each other. We can optionally have any number of slaves for reads, and we would use some sort of manual or scripted automatic failover, manual, scripted, or automatic, maybe heartbeat-based failover to actually achieve the failover itself. That's normally done through IP takeover, but there are probably a dozen ways that you could actually do a failover between dual masters. The pros of using dual master for HA, the configuration is actually quite simple, and generally if it's simple to understand and simple to configure, then it should be simple to maintain, and you have lots of extra options in administration. It's very, very simple to the basic master, similar to the master-slave configuration, and since many people are already using that, it's just sort of natural to say plug it in the other direction. It's actually just one additional command to get it running in dual master instead of master-slave. It allows you to easily fail over in either direction, so it's not one way. A typical question actually is, if you have master-slave versus dual master, why would you ever configure dual master rather than just failing over to the slave? Any ideas why? And actually, we can make this one worth something. Your choice of either a nice card or a poster for statements or functions.
Oh.
Yeah, if you've worked at Yahoo, you don't count. Okay. So,
you want to keep...
Someone who hasn't gotten anything yet. What? Have I given out too many of these things? Go ahead.
Slave has a different bin log IDs than the master, so when you fail over to slave, you don't know where to start the slave back up to catch it.
I think so, sort of. Can you clarify?
The master failed.
So you have a single master, single slave, and the master fails. So you start pointing applications at the slave.
Everything's okay. But when you bring the master back online, you have to get its data catch up back to the slave.
Very good, yes. So the process of actually bringing the original master back is infinitely more difficult. And the reason for that is that basically, if the slave is not replicating to anything else, and I guess you could, given enough time, you could definitely get it back. Potentially without downtime. If you have a good backup of the slave, and you actually note the position in the binary logs when you do the failover before you start writing anything, you could recover it. But it isn't sort of built into the system, and it isn't automatic in any way. It's not just turn it back on and it starts working again. So there's a lot of additional reconfiguration, there's a lot of additional stuff. And you can come up here when we're done and get out of base. Okay, so basically using the dual master configuration, like I said, it doesn't buy you any scalability for writes, doesn't buy you any capacity. What it buys you is sort of an easy configuration to be able to fail over in either direction. So once you've failed over to the second master, and I usually just call them A and B. So you have master A, you have master B. Once you've failed over to B, there's nothing keeping you from failing back to A because it's in the same exact configuration as A to B was. A to B and B to A are identical. In general, they should be identical hardware, identical configuration. absolutely identical to each other. Yeah?
How are the bin logs identical?
The bin logs are not identical.
Which means you can't reslave any slaves with them.
Correct, which means slaves of the dual masters you cannot move.
So they're down until you brought up the one that's down.
Yeah, so if you're dependent on having lots of slaves to scale reads, for instance, then you have to think a lot more about it. But it's no more thinking necessarily than you would have had with a single master. So if you have 10 slaves, you would probably connect 5 of them to one master and 5 of them to the other. That way you always have a slave that you can reclone to the other 5 if necessary. So if one of the masters failed sort of irrecoverably and you had to rebuild its RAID or something, so it's going to take a while, you have 5 slaves still left. You could take one of those 5 slaves and clone its data to the other 5 that are currently offline and get them all running against the same master again in a master many slaves scenario until you fix the other master. And you can then use any of those 10 slaves to fix the data on the dual master, provided that you're not doing any filtering. One of the interesting pros of this model actually is that it allows you to do sort of online schema changes without downtime. One of the big problems in MySQL that comes up over and over again, another one of these sort of every user conference so far it's been, that will eventually be fixed, is that alter table. What's wrong with alter table?
Takes forever.
Takes forever, locks the whole table, makes a complete copy of it. Bad things, right? You can never do it in production, ever. There are a couple of very simple cases where you can do it in production. Go ahead.
But isn't the case where it's only blocking writes, it's not blocking reads?
So
not really.
It blocks reads.
So because of it blocks writes, and it doesn't block reads up until the first write request, because once the first write is in the queue for that table, no other reads get processed until that write gets through. So in reality, technically, yes, it only blocks writes. In reality, it blocks everything. Why that is, actually, I'm not entirely certain. Why the queuing has to, I mean, that could be a special case in the queuing, but the special case should actually just be to fix alter table. And that's a much harder thing to do, so it hasn't been done yet. But in this model, provided that your changes are non-destructive and that the same query text will run on both master and slave before and after will run both before and after the schema change, you can actually use the dual master model. There's a command called set SQL bin log equals 0, where you can disable binary logging for your session. So by connecting to the inactive master, running set SQL bin log equals 0, you can then make any number of schema changes that don't get replicated to the other master. So at that point in time, it's behind a little bit because of the schema changes, and some of them are in process and such. Once all of those are done and you're happy with the new schema, let it get caught back up with replication. Do a sort of gratuitous failover, casual failover to the other machine, and do the exact same process there. So if you imagine you have 300 gig worth of data and you need to build a new index, that's an ugly scenario if you have a single master, right? Because it takes potentially many hours to build that index, partly because of alter table not being very nice, and partly because of just the size of the data. But with a dual master scenario, you can do that with actually no user visible downtime. The only problem with the model in that scenario is that you lose some of your failover ability while you're making those changes. But that's no worse really than if you had an actual failover and you were running on a single master for a while. Yeah?
What happens in the scenario where the master does an update, the bin log isn't caught up on the slave, the master goes down, and then now your new master moves forward?
Correct. So there's a couple of sort of caveats, and actually, next slide. Dual master cons. The first con, like I said, it doesn't help you scale writes at all. Regardless of how you might think about it, it really, the machine is doing the same work, and it can always be done more efficiently in a multi-threaded fashion generally than it could be done in a single-threaded fashion. It's limited to 2 sites, but the biggest one is that replication is asynchronous, so your dual master may get behind. So there's always a chance of data loss, although in production systems and in reality the chance is fairly small. And that's one of the trade-offs that you have to make generally in any sort of scalable production system, there's always a trade-off between sort of minute or maybe not so minute data loss versus absolute scalability and performance and everything else. So usually the trade-off here is basically data loss versus performance. And in replication models and database replication models, you could have a system where you could never lose any data, but the performance may not be as good, because the way that you guarantee that you don't lose data is that you have to update another system as well. And waiting for that other system to reply adds an inherent delay in acknowledging the original request.
So it's purely writes over the old data as opposed to gagging when it can't correlate between the differences?
Correlate between the differences, what do you mean? So there's a couple of caveats, I would say. If you use dual master in production, the normal recommendations that I would make is set up both machines in read-only mode so that they start up not accepting writes at all, and set them both up in skip slave, I think is the I always mix it up, skip replication or skip slave. Skip slave start, that's the one. That tells it not to start replication on startup. What that buys you is the ability to, if you have a failure of one of the machines, cut the power on it. So let's say you can't access it because it's freaking out and swapping or something like that. So it's effectively down, but it's not really down. The worst case scenario is that it comes back and automatically starts accepting stuff, or that it has stuff queued that get fed directly into production that you haven't sort of verified. So that by setting it to start up and read only, and by setting it to not start replication, you can effectively fence it on failure. So if you think it's dead, you're going to fail over anyway. You cut the power, reboot it effectively. When it comes back, it will come back in a known good, read-only, non-replicating state. So you can then manually inspect it, and if nothing has been lost or nothing has been, there are no differences from the point that you failed over to the point that you started, you can just restart replication and it will catch up. If there are differences, you can either manually resolve them and fix it, or just reclone the data from them. So let's say you accepted 5,000 writes because replication was delayed at that moment in time. Depending on your application, you can either say manually merge them, manually inspect them, and then let replication just take them, or you could just throw them away, depending on the application.
So when a slave's behind, that doesn't necessarily mean that it's not receiving all the transactions. It usually means that the SQL thread is behind in applying the logs that are already on that slave to the actual table.
Yeah, so I would say that in a production scenario, you will, in most cases, only be behind receiving from, you only be behind executing from the local logs on the slave. You won't be behind receiving from the master. So once the master has officially sort of failed, you may still have all of its log events on the slave, and you're just behind executing them. So once you catch up executing them, you haven't lost anything. The typical transit time for a write to be accepted on the master, committed, and then available in the log on the slave is way less than a millisecond. On a local gigabit network and all of those caveats, but yeah.
So on someone casual failover, when you're just doing it for schema change purposes or whatever, I mean, you can still lose it. I mean, okay, but you could lose.
By sort of coordinating the changeover, you don't have to lose anything, actually. The coordination that you would do is using IP takeover. You first set the target machine to be you first set the current writable master read-only, and as long as your application can handle getting back, server is read-only as a response to a write, it can retry that write, so you get a chance to get them caught up before you actually make the switch. So you get them caught up, you do the IP takeover with a gratuitous ARP, and then you remove read-only from the target machine. And you haven't lost anything, and provided that the application gracefully handles the read-only case, the worst that users have experienced is usually less than a second of delay. So we actually have 10 more slides to go, and 3 minutes. Hold the question. We got a couple more scenarios in HA to talk about, which we won't spend too much time on. But some other options you have, you can use SAN solutions for high availability of the master side of things. What this gains you is not having to buy disks, basically. Rather than having two completely independent storage systems, you can consolidate some of that storage onto either a single or multiple SANs shared amongst many masters, or just a single SAN shared amongst 2 masters, just so you don't have to buy 2 of every disk effectively, well 4 in the case that you use RAID 10, but duplicates of the data. This is an okay concept, and it has some ups and downs. You normally use heartbeat-based failover and fencing and such to mount the SAN on the target machine when there's an actual failure. The pros there is basically you have a single copy of the data, so particularly if you have very large databases, the storage cost could be reduced versus buying 3 terabytes of disks for two separate machines. It may be easier just to buy a single set of 3 terabytes of disk data. You don't have to worry about replication getting behind because you're both writing to the same source. There is a single SAN, but that SAN system is a single point of failure as well. So, depending on the application, SAN systems could actually give you better performance. Again, it's very dependent on the application. Particularly spending the same cost as you would on 2 separate RAIDs, you may be able to buy, again, depending on how you configure this thing and how good of a deal you have with SAN vendors, you may be able to buy a single SAN system that gives you better overall performance across all systems than each individual system would get. The cons there, you have a single copy of the data, so any sort of corruption whatsoever, basically you lose your only copy of the data. In the replicated model, you always have 2 separate copies of the data, so if MySQL sort of goes bonkers and corrupts things, provided that it isn't something that's replicated that corrupts something, then you haven't lost anything. And in typical cases, that's not going to occur. Most of those sorts of corruptions that would ever occur would be due to some sort of machine failure, or like a RAM failure, for instance, that caused weirdness to be written to the disk, something like that, RAID controller failure. So it's isolated to the one physical machine. In this case, it could very well be, RAM failure would actually corrupt the data on the SAN because it's your single copy of the data. Cost can be prohibitive, but you probably already knew that just based on the word SAN. Fiber channel addition especially requires lots of additional infrastructure to get it to get it in any state where it's anywhere near resilient. So that's a huge cost. iSCSI can be fairly nice there, but latency is higher and all of that. So you can't do any sort of schema change tricks because there's only a single copy of the data and a single MySQL server running at any time, so none of that stuff works. DRBD, there's actually a session, or maybe even 2, about DRBD 3.3 at the conference, so you can go there to learn lots more details, but it's basically a software SAN solution that's block device level replication between 2 systems with their own independent storage. And you would typically treat it as though it were a SAN, even though each machine really has its own disks. So you use simple hardware and infrastructure using locally attached RAIDs, same as you would with dual master, same hardware, different software. The cons, though, it's fairly complex to configure and maintain, I would say. It may cause performance problems, especially if you haven't configured it right. Because it's a software solution, it's replicating things the same as MySQL is. So it's subject to some of the same problems as MySQL replication is. One of the interesting things is that since it's basically synchronous replication, any problems with the mirror can cause problems with production. So, and depending on protocols and stuff, there's lots of configuration options you can choose to trade off on this. From the software perspective, there's still a single copy of the data, so that copy may get corrupted. And again, no schema change tricks are possible because of the single copy of the data and a single server running. So to put it all together, typical solution, you want to combine the partitioning solution with the HA solution in a meaningful way. Partitioning solution just treats the shards or partitions as a single MySQL server. It doesn't really care if there's HA behind that. In reality, you probably would have it. HiveDB plus dual master, in my opinion, is a pretty darn good solution for most applications. It's not technically perfect. There's a chance of small data loss. There's all of this stuff, but administratively, it's very simple to maintain once you get it running. And configuration of it initially is also quite simple. So overall, just getting it going, keeping it going is very easy. You can use LVM for volume management, which gives you the ability to snapshot the 2 machines and do a lot more interesting administrative things there. So the combination of HiveDB plus dual master replication plus LVM, you'll spend almost no time administrating anything. I promise. Okay, any questions? Any topic overall? Just general discussion. We'll go ahead and end the official session. We're 1 minute over, I think, but good time. And I'll stick around for a little while, so if you have any questions, feel free to come up and ask.